Hi everyone, my name is Jędrzej Kozrawski and I'm here to present our work titled BLT, Balancing Long-Tailed Datasets with Adversarially-Perturbed Images. This is a joint work with Victor Fragoso, Nikolaos Karianakis, Gareth Mittal, Matthew Turk, and Mei Chen. To start, let's establish what long-tailed datasets are. We're talking here about large-scale datasets with many different visual categories, where some classes are common and have a lot of training examples per category, and many classes are rare and have only a few examples. The exemplary distribution is seen on the right based on the iNaturalist 2018 data. In this work, we're adopting previously established standards where the training set is imbalanced while the validation and test sets are balanced. This is done to ensure that the performance metrics used will equally reflect the recognition capabilities of the classifier regardless of the category being rare or common. Additionally, apart from analyzing the performance on the test set as a whole, we're going to analyze the performance of the classifier on subsets of the test set consisting of only many-shot categories, those with more than 100 images per category, medium-shot categories, those with 20 to 100 images, and few-shot categories, those with less than 20 images. This procedure is done so we could analyze the behavior of the proposed model in more depth. Based on this division, we can see that modern approaches for long-tailed datasets have rather poor performance on tail categories and focus on achieving high overall accuracy. This behavior is visible here on two benchmark datasets for long-tail recognition, ImageNet LT and Places LT. In our method, we decided to focus on increasing the few-shot accuracy while preserving high overall accuracy. Our proposed method consists of three main modules: a hard example hallucination module, a custom sampler, and a squashing cosine classifier. We'll discuss the modules and their properties on the next slides. So let's talk first about the most important aspect, hard example hallucination for the few-shot categories. The idea is to generate on the fly for every batch additional images that would act as hard examples, forcing the classifier to adjust and thus lead to the increase in the accuracy for these categories. So first, after creating a batch of images through sampling, we randomly choose a fraction of the few-shot or tail class images to hallucinate. For example, a cheetah in this case. Next, using a confusion matrix computed during a validation step, we're sampling a class that is being currently confused with the sampled tail category, for example, a tiger or a cat. Next, using a gradient descent image generation, we're adding a small perturbation into the tail image, cheetah, so that our current classifier would misclassify it as our target category, a cat, or with some minimum confidence threshold. Finally, we're adding the newly hallucinated image to the current batch and proceed with the training process as usual. The difference being now having more images in the batch that are specifically tailored for the benefit of the few-shot or tail categories. Two additional modules that help to maintain the balance between a few-shot and many-shot accuracies are the batch sampler and the classifier. We've used here a custom batch sampler that samples categories with a probability pi proportional to the weights wi assigned to every category I. Higher weight means higher probability. The weights are inversely proportional to how many images ni each category I has. Fewer images in a category, the higher probability of it being sampled, with one caveat being the hyperparameter gamma in the denominator. Gamma equal 1 means standard resampling. Gamma equal to 0 means no resampling. All categories are sampled with equal probabilities. Gamma smaller than 1 favors more common categories, and gamma higher than 1 favors more the rare categories. We've also adopted and parameterized a cosine classifier to increase the performance of the overall model. The classifier has two hyperparameters, alpha and beta. In this formula, WC is the weight vector of the classifier for category C, and X is the feature vector of an image. We show the impact of all the hyperparameters in our ablation study. Here, we present the results on two standard benchmark datasets for long-tail recognition, ImageNet LT and Places LT. All the methods presented use the ResNet 10 backbone and are trained from scratch. we can clearly see that our approach significantly outperforms all current approaches on the few shot categories by at least 7% on ImageNet LT and by 1.3 on Places LT, while simultaneously increasing the overall accuracy achieved across all categories. Here we can see 3 ablation studies performed on the ImageNet LT. On top, we have the impact of the hyperparameter gamma on the accuracy, where we can see that with an increase in gamma, we observe a slight increase in the few shot accuracy, while observing a simultaneous decrease in the many shot accuracy. On the bottom, we see an ablation study on 2 hyperparameters of the squashing Gaussian classifier. We can observe a similar balance between many shot and few shot accuracies. With an increase in alpha, many shot accuracy rises, but the few shot accuracy decreases, with the opposite behavior observed while the hyperparameter beta increases. Based on the observed data, we decided to choose alpha equal 20, beta equal 0.5, and gamma equal 0.9 for the experiments, since it yields a high few shot and high overall accuracy. One very important question that needs to be answered is, for every batch, how many hallucinated few shot images to add? We performed an ablation study on the ImageNet LT using a hyperparameter P that reflects what fraction or proportion of few shot images present in the current batch should undergo the additional hallucination step. The more few shot images being added, the better the accuracy for few shot categories, but slightly smaller the accuracy for many and medium shot categories. Based on this, we choose P equal to 0.5. The second important question was whether the increase in the few shot accuracy was in fact due to the proposed hard example hallucination procedure, or can it be substituted with additional oversampling with traditional augmentation methods. On the plot below, we can see the comparison between a plain model with sampling, baseline, our approach without adding hard examples to the batch, deemed neither, our approach with additional augmented few shot images in the batch, deemed augmentation, and our proposed approach with additional hallucinated hard examples in the batch, deemed BLT. We can see that simply oversampling the few shot categories to match the number of images as in BLT does not increase the accuracy for few shot categories, thus providing stronger support for the necessity of the proposed hallucination technique. We've also compared our method across different backbone architectures. In the presented table, you can see the results on the ImageNet LT dataset for 6 different backbones for the plain model with sampling baseline and our proposed approach. Based on the presented results, we can see that while increasing the model complexity might result in a higher many-shot accuracy, even with a simple baseline, it is not the case for the few-shot accuracy. BLT consistently increases the accuracy for few-shot categories for all the backbone architectures. To sum up, we're providing a novel batch augmentation technique that uses a targeted gradient descent image generation technique to hallucinate on-the-fly hard examples for few-shot categories. The proposed approach can work with any backbone architecture. We provide a deep analysis of utilized hyperparameters and their impact on the model performance, as well as thorough ablation study. The code is available under the following link or through the provided QR code. Thank you.